And Dr. West, we're honored to have you here and welcome to the club. And you have the floor.
Okay, thanks. Thanks very much, Mark. I'm just trying to get my PowerPoint to work right. Let's see. Weird. Let's try this. Okay. Yeah, thanks very much, Mark, and everyone for inviting me. It's my pleasure to be here tonight. What I wanted to do was just give kind of an overview of our current understanding of what we think the universe looks like on the very largest scales. This is one of my own particular research interests. And it's a pretty exciting times as we get to understand, where we're located in the universe and what our surroundings actually look like. I thought to start, though, I'd actually tell you a little bit about Lowell Observatory. I assume some of you are familiar with Lowell, some of you might not be. So just to give you a quick overview of where I work, Lowell Observatory is located in Flagstaff, Arizona, or about 2 hours drive north of Phoenix. We're in 7,000 feet elevation, so we're not like the rest of Arizona. It's cool. This is a picture I took of a typical snowy winter day, and it's really beautiful out here. We're here because of Percival Lowell. He was, oops. Sorry, there we go. He's our founder. We're named for him. And he was a rich amateur astronomer from Boston, essentially, who was fascinated by the possibility of life on Mars. And so he ended up building an observatory out here to try and map the canals of Mars, which was a popular idea at the time, that there was an advanced civilization of Martians who were on a dying planet and needed to transport water from the polar ice caps. And so he would make these very detailed drawings of the canal of Mars as he saw them. And he was in some ways the sort of the Carl Sagan or the Neil deGrasse Tyson of his day. He was a great popularizer of astronomy. He wrote a lot of books. He wrote a lot of magazine articles. He really helped popularize, in particular, the idea of life on Mars all around the world. So in 1896, he commissioned a telescope to be built out here in Flagstaff. And it is a 24-inch telescope. This is what it looks like today. You can go visit it. We have tours. It's the 24-inch Clark telescope built by Alvin Clark and Sons. And he would use this to, as I said, map the canals of Mars. By the way, this is the 125th anniversary of the telescope. So we're having a bunch of special events, including later tonight. There's actually a talk, a live stream from out at the telescope. If you're interested, Lowell has a YouTube channel. You can always find more things there. So this is what it looks like today. It's just gorgeous. It was refurbished. It's got lots of brass. The inside of the dome is, I think, amazing. It's just this beautiful wooden structure. It's a really, really beautiful telescope. We still use it for public stargazing. People come in and they look through it. Outside the pandemic, of course. Actually, even now we have it open for small groups and tours. And this is a picture of Percival Lowell as he would observe with it. And so you can see he had this really nice chair arrangement so he could be raised and lowered as needed to look at different elevations. Now, Lowell Observatory is probably best known for the discovery of Pluto. In 1930, Clyde Tombaugh was a young astronomer here, and he was tasked by Percival Lowell with finding planet X, as it was called back then. And so in 1930, using this telescope, he discovered this hypothetical planet and, became world famous, obviously. But it's not the only thing that Lowell Observatory is known for. In the decades before, Vesto Slipher had a spectrograph out here, and he actually made the first observations of the expansion of the universe. He was the first person to get spectra of the nebulae, as they were known back then, galaxies as we know them today. And Edwin Hubble actually came along and used most of Slipher's data, along with some of the data that Hubble himself had taken, to show that the universe, galaxies seem to all be receding from us. But in fact, the very first observations of several dozen galaxies were done by Vesto Slipher right here at Lowell Observatory. Also, Vera Rubin, actually yesterday was Vera Rubin's birthday. Fortunately, she died 5 years ago. But Vera Rubin was a pioneer in the study of dark matter, and she did many of her early observations right here in Flagstaff. This is her using one of our telescopes a little bit outside of town. So a lot of pioneering work on the existence of dark matter was also done here. Today we have a state-of-the-art 4.3 meter telescope that we call the Lowell Discovery Telescope. This is a photograph of it. And again, you see we do get snow out here. It's a state-of-the-art facility. It's the 6th biggest telescope in North America. And Lowell astronomers get a lot of time on this. It operates 300 nights a year. It's closed at the moment because we do maintenance every year, and we do it during the rainy season, which is now basically. But in general, it observes 300 nights a year. We have very dark skies out here, which is great. This is what the telescope looks like. As I said, it's 4.3 meters. It's the Ritchie-Chrétien design. So the instruments hang off the bottom. I don't know if you can see my mouse down here. And we've got a pretty sophisticated suite of instruments, and new instruments are being built now as well. Because it costs $53 million to build, so we share this, or we sell nights to other universities that want to use it. So our partners at the moment are Boston University, University of Maryland, Yale University, Northern Arizona University, which is located here in Flagstaff, and the University of Toledo. These are all our partners in the telescope. We also have a couple of smaller telescopes located about a half hour outside of Flagstaff. We have a 42-inch telescope. We have a 31-inch telescope, which is in very sorry shape. So we're actually replacing it with a brand new 1 meter plane wave. And we also have an interferometer. Again, interferometer works. It combines the light of several smaller telescopes to act like one large telescope in terms of resolving power. So we share this interferometer with the Navy out here. The U.S. Naval Observatory has offices and a telescope out here as well. So that's another thing that we're involved with. And we just recently got an $8 million upgrade from the government to improve this facility. So that's pretty exciting. We're also, because of our legacy from Percival Lowell is also one of public outreach. So we do a lot of outreach. It's another important component of our mission. And we're in the process of really ramping up our public outreach efforts here. At the moment, pre-pandemic again, we get more than 100,000 visitors a year come up to Lowell Observatory here in Flagstaff. And we're aiming to double that, which we can easily do if we just have the space and the facilities for that. So we recently opened what we call our Giovanni Open Deck Observatory. This is a photograph taken. This is Comet Neowise when it was visible. And these are little glow stones which sort of mark your way up in the dark. It's really beautiful. But the Open Deck Observatory looks like this during the daytime. There's 6 telescopes, and they're open for the public. You can come and look through them. They range from a 5-inch refractor to a 32-inch Dob. And there's 2 of the telescopes. One actually has a spectrograph on it. One has it's called a Malan-cam. It's a really sensitive kind of webcam to take digital images. But the other ones you can look through with eyepieces, and they're really spectacular. It's one of the best facilities, I think, anywhere that the public can come look at the telescope. So if you ever find yourself in Flagstaff or in Arizona, you're most welcome to stop by. This is what we call our Moonraker telescope. It's a 6.6 inch, if I remember right, refractor, and it's got a steampunk look. It's got like a Victorian design. It looks really, really nice, and the optics are great. In 2023, we're going to have a brand new science center called the Lowell Astronomy Discovery Center. And again, we anticipate welcoming more than 200,000 visitors a year. And it is just to teach people about astronomy, about our place in the universe. So this is what it will look like when you come in. We're trying to do something really unique here, something really different that you don't see at every other science or astronomy center. We're going to tell, for example, the story of your atoms from the Big Bang to today, and maybe where they're going in the future. So this is what some of the exhibit halls might look like. We don't have a planetarium per se, but we're going to have a 180-degree theater with a partially dome as well. So it's going to be really spectacular for showing different kinds of shows and events. Because we have such dark skies out here in Flagstaff, we're the first international dark sky city. Uh, Rather than building an indoor planetarium, we're going to take advantage of our dark skies, and our planetarium is actually on the roof of the building. And we're going to use the true night sky as our planetarium, much like, if you ever go out to the University of Texas, they've got their open sky planetarium out there. And so that's what we're going to do as well. The seats will be heated, by the way, because it gets a little chilly at nights here in Flagstaff. So it'll be a really cool experience for people. And we even have something we call our diverse universe wall, which is going to feature biographies of 70 astronomers from around the world. And the idea is to inspire the next generation of kids. So it doesn't matter what's your background, it doesn't matter what country you grew up in, it doesn't matter what disabilities you might or challenges you might have faced in your life. There's a place for you in astronomy too. And that's the message we try and get across by showing biographies of 70 different astronomers from, I think, 33 different countries, I forget. So that'll be a nice component of this as well. And finally, since I'm finishing talking about Lowell, if you're interested, we have these things called astro alerts, and the place to sign up is in the upper corner. We send out these, when there's an interesting news story, we send out an alert to people with some links to places to find more information. So here's a couple of examples of astro alerts. I do these. So you're welcome to sign up for free. We try and do news stories that aren't necessarily the things you see all the time on CNN or something, maybe a little bit more offbeat sometimes. So if you're interested, you're welcome to sign up for that as well. Okay, so anyway, let me get to the topic at hand. And this is an overview of what we think the universe looks like. And by the way, I'm happy to answer any questions you might have. You can put them in the chat. I can't see them until the end, unfortunately, but don't hesitate to ask. So this is what we thought the world looked like in 1570, right? This is a map that was made. And as you can see, it's not bad. Africa looks pretty good. North America looks odd. South America looks kind of pathetic, but it's got continents, and it's sort of a first view of what we thought the Earth might look like, right? And it's very hard, of course, because this required people to sail all over the world and try and piece together what Earth looks like while you're on its surface, essentially. It's a very difficult challenge. So, less than a century later, this is a map that was made in 1664. And you can see, all right, things are getting better. South America starts to look like South America. North America is not complete, but it's getting there. Europe, Asia, Africa, those are definitely looking a bit better. Come 1794, that's a pretty good map, right? And so step by step, piece by piece, by learning, by piecing together data, map makers were able to make a better, more precise map of what our world looks like. In astronomy, it's the same challenge that we face. We think of astronomers as stargazers and scientists, but in many ways, we're map makers. We're trying to map the universe in our own cosmic backyard and on the very largest scales. And it's the same kind of challenge. We sit in one location of the universe, and we're trying to figure out what it looks like on much, much greater scales, much vaster distances. And that's really hard. This is the earliest known depiction of the earliest known map of the universe, if you like. This is the Nebula sky disk. It was made by Bronze Age people 4,000 years ago. It was discovered in Germany near the town of Nebula. And this is the earliest known depiction of the night sky and the universe. You can see obviously the sun and the moon. You see this clump of stars here, and this is the Pleiades, basically. This is what people noticed in the sky, and this is the first depiction of this. So here's the Pleiades up here, obviously. So pretty cool from 4,000 years ago. Here's a star map from China, circa 600 AD. And again, you see, different groupings, different constellations, but this was a map of the heavens that people produced back then. This is a Pawnee sky chart from a few centuries ago. Again, each of these little dots or crosses depicts different stars and different groups of stars. You can see them here. This was a map of the heavens. This was all done by naked eye, of course. This is all that people could see at the time. In the 18th century, William Herschel, famous astronomer you all know, decided to try and map the universe. And the way he tried to do this, he said, I'm going to assume that all stars have the same intrinsic brightness. And so the ones that look fainter must be further away. And so by mapping stars in all directions of the sky, and assuming the faint ones were further and the bright ones were closer, he came up with this map of the universe. Nobody knew there were other galaxies at the time. And lucky for us, we happen to reside at the center of the universe because that's what his map showed, right? So that was, I mean, it's a clever effort. It was a good attempt. The problem was, so here's where the sun would be located. The problem was basically incomplete data. Herschel didn't know about all of this dust that exists throughout the Milky Way. And his dust is like trying to look through a fog or like trying to look through a forest fire, smoke. You can only see so far, and then you can't see any further. And so the piece of the universe that Herschel thought he was mapping was actually just a small piece of our Milky Way galaxy. And so he didn't realize he couldn't see it. So that's why it seemed like the sun was at the center, because you could only see so far around. So if we could see the Milky Way from far off in space, we now know it would probably look something like this. Beautiful spiral pattern. We think there might be a bar at the center of the Milky Way, and the sun is kind of in the suburbs about 2/3 of the way out. Here's a beautiful image that was just published last week. Oh, so here you are here. Here's a picture that was published just last week. You probably saw in the news that the Hubble Space Telescope was down for a few weeks. They had technical problems with the computer. They just fixed it a few days ago. And this is one of the first images that they took with the revived Hubble Space Telescope. I thought it's a beautiful, beautiful galaxy. And it probably looks a lot like the Milky Way would look like if you could see it from space as well, right? So again, the sun would be somewhere out here, near the edge of one of the spiral arms, basically. So beautiful, beautiful image. Now the Gaia spacecraft has been
What was that an image
mapping
of?
the Milky. Sorry?
What was that image of that previous galaxy you just showed?
I don't remember what the name of the galaxy is. I'd have to look it up. It must be an NGC galaxy, but I'm not entirely sure. I'd have to find it. So Gaia has been busily mapping the Milky Way galaxy for the last few years, and it's on a sort of 5-year mission. Gaia's great strength is it's above the Earth's atmosphere, and it has exquisite astrometry. It can measure the positions of stars to incredible precision. And so it's been busily producing the most detailed map of the Milky Way yet. This is our view from here in our solar system, of course. We're looking towards the center of the Milky Way here, getting to see all this dust, which is just the ashes of dead stars, previous generations of stars. You see the large and small Magellanic Clouds here. These are small galaxies, of course, that orbit the larger Milky Way galaxy. So this is our current view of what the Milky Way looks like. And every year, Gaia is taking more and more data, more and more images that will just improve on this map and give us even more detailed information about our home galaxy. But, for more than a century, people knew about these fuzzy objects in the sky, right? We all know about Messier's work, and Messier was a comet hunter, but he found all these fuzzy objects that were in comets, and he had no idea what they were. And these things came to be called nebulae, for the Latin word for clouds or fog or mist. And so this is a drawing from 1847 of one of these nebulae. Here's another image from 1845. Nobody knew what these were. Some people thought these were solar systems in the process of being born nearby in space. Others thought these were what they call distant island universes, way, way far away, much like our system of stars. But nobody knew for sure. Here's another drawing of one of these nebulae that appeared through a telescope in 1849. Edwin Hubble came along, and he was the first person to show that these nebulae, not all of them, but many of them, were in fact distant island universes. These things were way, way beyond what we now know as the Milky Way. These were other galaxies, essentially. And Hubble did this in the 1920s. This is a picture of the Andromeda Nebula, the Andromeda Galaxy. And he found that there were certain variable stars, stars whose brightness changes periodically. He could compare them to stars in the Milky Way. And by measuring their relative brightness, he could get a distance for the Andromeda Nebula and its variable stars. And he found that this thing was way, way beyond the edge of our system of stars. And so today we know that the Andromeda Galaxy, we call it, is about 2 million light years away, right? So when you go out and see it at night, and again, here in Flagstaff, I can see it with the naked eye when there's no moon up. Our skies are really dark. It's 2 million light years away, so the light you see obviously traveled for 2 million years to reach your eye any night that you see it. This is a really cool picture, I thought. This is taken by a photographer, Ralph Rohner, who set up his camera, took a stacked long exposure of the Andromeda Galaxy, you see it here, and then took a shorter exposure of the landscape, the foreground, and just pieced them together. But this is all to scale. And the Andromeda Galaxy is huge, right? It's bigger than 5 full moons on the sky, but it's just such low surface brightness. It's so faint that you can't see it very well with your naked eye. All your eye can really pick out is the very brightest central region. Even your telescope only picks up the very innermost regions, but it's huge. By the way, I just going to mention this guy, Ralph, also is today's astronomy picture of the day. If you didn't see it yet, it's pretty cool. This is taken from an airplane cockpit, and it's got everything, right? It's got stars. It's got stars. It's got the aurora. It's got clouds. It's got city lights below. It's a really, really cool picture he took from an airplane cockpit. So it's today's astronomy picture of the day. So we now know not only that there are other galaxies out there, and Andromeda is our closest big neighbor at about 2 million light years away, but we also know that we're on a collision course with the Andromeda Galaxy. The Milky Way and Andromeda are going to collide in about 4 billion years. This is a computer simulation showing what we think is going to happen. So, in a computer simulation, you just put in, stars, and eventually you let gravity do its thing, and you see what happens. So here's the Milky Way. The Andromeda Galaxy will appear over here. Sorry, my computer keeps forwarding, so let's try this again. So the Andromeda Galaxy will appear in a second again. And the other small galaxy you'll see near it is the Triangulum Galaxy, M33. And so gravity is relentless. Gravity is going to bring these two galaxies together. And in about 4 to 5 billion years, which will be interesting times because that's when the sun will be swelling up and dying, so probably engulfing the Earth at some point. Andromeda and the Milky Way are going to pass through each other. Look how the stars spray into space. They carry off some of the energy, some of the angular momentum. Gravity is going to bring these two galaxies back together. And now they're going to quickly settle down. And it's time in the bottom right, by the way. So about 5 billion years from now, they're going to settle down into one larger galaxy that astronomers have already cleverly named Milkomeda. And that's what we think will happen. And so our sun will be one of, hundreds of billions of stars in this new larger galaxy. One of the things people often ask is, will stars collide, for example, when this happens? And the answer is no. You can do a calculation that shows when two galaxies collide, like Andromeda and the Milky Way, the odds of any two stars hitting is virtually zero. To give you some perspective, if you got in your car and you drove 60 miles an hour right now to the sun, it would take you about 177 years of nonstop driving. If you drove in that same car to Alpha Centauri, it would take you 50 million years. And that's our nearest neighbor star, right? So there's so much space between the stars and the Milky Way that the odds of any of them hitting when Andromeda and the Milky Way collide is zero. So what will happen is the sun, with all of its planets in tow, will just become part of this new larger galaxy. But again, the sun will be swelling up and incinerating Mercury and Venus and the Earth and maybe Mars. And it'll be really interesting times for whoever's around here then, but that's kind of our future. So of course, we now know that there are just countless galaxies out there. This is called the Hubble Ultra Deep Field. You've probably seen this before. It's a tiny region of the sky. That little red square at the bottom left shows the area of the sky that this image captures. Just as you know, with your camera, if you keep the shutter open, the longer you keep it open, the more light you record, the fainter you can detect objects. The Hubble Space Telescope kept its shutter open for the equivalent of 11 days. It was 400 orbits around the Earth, just recording light. This particular piece of the sky was chosen to be a really boring piece of the sky where there's nothing known. There's no star clusters. There's no interesting galaxies. It's a random piece of the sky. And this is what it looks like. This is kind of a zoom through, if you like, looking at the galaxies at different distances. And so within this small area of the sky, the Hubble telescope detected more than 10,000 galaxies. So if you realize that this is just a tiny piece of the sky, and if you assume it's a typical region and you extrapolate over the whole sky, it says that there are hundreds of billions, maybe even 1 trillion galaxies in the universe, if you consider the fact that there must be galaxies even fainter, too faint for Hubble to see at these great distances. So it means that the universe is just chock full of galaxies, probably as many as a trillion or so. So if you think about the Earth, if you were an alien and you come to Earth, the first thing you might notice is at night, all the lights distributed across the surface of the Earth. And of course, this would tell you where human beings live. And the human beings live on land. So the lights would map the way the land is distributed on the Earth, right? And so in a sense, we can do the same thing if we want to say, well, how is matter distributed throughout the universe? We can use the light of galaxies as a way to map that as well. And so that's what we do. One of the things we find, for example, is that galaxies are very gregarious. Galaxies like to be near each other because of gravity, basically. So this is a famous Stephan's quintet. And you see these galaxies are, 4 of them at least, are actually near each other in space and are interacting with one another. This is another beautiful example of a few galaxies in the process of colliding. And again, if you come back in a few billion years, and I encourage you all to do that, this will probably be one larger galaxy at that point. We know that we live in a small village of galaxies that we call the local group. Astronomers aren't really clever with their naming. So we live in the local group, our little village. It has about 3 dozen, maybe up to 4 dozen galaxies are known at the moment, and new ones are being discovered all the time, but they're small. The biggest galaxy in the local group is Andromeda. The second biggest is us, the Milky Way. Third is M33, the Triangulum galaxy. Then there's loads of these little dwarf galaxies, and they kind of swarm around the Milky Way, and they swarm around Andromeda in the same way that bees swarm around a hive. And these dwarf galaxies, we know, are the most common kind of galaxy in the universe. But we live in a small town, essentially, if you like, called the local group. Again, several dozen galaxies. But there are bigger, just as there are bigger towns and cities and metropolises, the same thing is true with galaxies. This is the Virgo cluster, is located about 50 million light years away from us. And it has many hundreds, probably 1,000 or more galaxies, all in a sort of gravitational dance around one another, and including some very large galaxies you're probably familiar with, like M49 or Messier 87, some of the biggest galaxies you can see with your telescope. So this is a large town of, it's like if you think about, if I'll use Michigan as an example, our local group is like Ann Arbor, and this is like Dearborn or something. But then you get on to even bigger systems like cluster. This is getting to like Detroit levels. The Coma cluster is located 300 million light years away, and it's got thousands of galaxies, all held together by gravity's pull. There's these 2 giant galaxies at the center, NGC 4889 and NGC 4874, and they're beasts. These are much bigger than the Milky Way. These are probably devoured dozens or hundreds of smaller galaxies over their lifetimes to grow to their bloated sizes. But these are the cities of the universe. Here's another example. A Bell 1689 is 2 billion light years away, so it's getting out there. And virtually everything you see in this image is a galaxy in this cluster. It's a really crowded city of galaxies. The only differences are you can see these little arcs, kind of long arcs, and these, of course, are gravitational. Funhouse of galaxies like this actually distorts the light of galaxies behind it, and so you get these beautiful elongated streams of light. Here's another example. A Bell 370 is located 4 billion light years away, and again you see, loads and loads of galaxies, and you see these beautiful arcs. These are more distant galaxies whose light has been distorted by the intense gravity of this massive system. So we see lots of these things, but to give you a perspective, if you look at a massive galaxy cluster or a city of galaxies like this, and you compare it to our local group, this is what our local group looks like. Here's the Milky Way, here's Andromeda, not much between us. But if you put that cluster, a Bell 370, between us, you'd have literally thousands of galaxies in the distance between us and Andromeda. So these are really densely populated regions of the universe. Here's an even more distant example. This is something my colleagues and I have studied with Hubble Space Telescope, max, blah, 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 located about 5 billion light years away. So we're looking quite far out into the universe. So as I said, galaxies are very gregarious. They like to congregate together in everything from small towns to giant cities of galaxies. Now, imagine walking down the streets of Detroit or New York or Tokyo, a busy city, and the odds of bumping into somebody goes up because there's just more people around. Well, the same thing is true with galaxies. When you're in a densely populated region of the universe, galaxies are going to bump into each other, and it doesn't usually end terribly well. Here's a beautiful example of a galaxy that has had an interaction with another one, and a huge stream of stars and gas and dust been pulled off as a result of this interaction, just because of gravity. This is one of my favorite pictures. This one's just beautiful. So this is a group of 3, probably 4, maybe 5 galaxies, and they're just tearing each other to pieces, basically, just stripping stars off of each other. It's really beautiful. Here's another example, 2 spiral galaxies in the process of interacting with one another. And again, eventually these will probably merge to become one larger elliptical type galaxy. Another beautiful example, again, 2 galaxies interacting in this long plume of stars being ejected into space as a result of the collision. So galaxies are not terribly nice to each other. They bump into each other, they rough each other up. This, another one of my favorite images again. This is the ghostly remains of a galaxy that strayed too close to this spiral or disk galaxy. So you're seeing something like the Milky Way edge on here. And this is all that's left of a smaller galaxy that got too close and was slowly flayed by the gravity of this larger galaxy. So it's like a jet fighter breaking up in flight. The pieces keep moving forward in the direction it was going. So these stars keep following the orbit that the original smaller galaxy was on, and eventually they'll disperse. But for a while, they just leave these ghostly glow, and that's all that's left of a galaxy that no longer exists, essentially. This is an image my colleagues and I took several years ago with the Gemini telescope in Chile. One of my areas of research is what we call galaxy cannibalism. Again, big galaxies eat small galaxies, gives them more mass, that gives them more gravity, that lets them eat even more galaxies. So these big bloated galaxies cannibalize their neighbors. This is a galaxy. We think this might actually be one of the biggest galaxies in the nearby universe. And you can see in the center, 1, 2, 3, 4, probably 5 smaller galaxies. This, I think, is actually a star, and that's a star. these are the partially digested remains of smaller galaxies that this beast has cannibalized. And in a few, hundreds of millions, billion years, what's left of these galaxies will also be torn apart, and their stars will just become part of this bigger galaxy. And that's how we think most galaxies grow. Virtually every big galaxy, including the Milky Way, has probably devoured dozens, hundreds, maybe even thousands of smaller dwarf galaxies during their lifetime. So it's a sort of galaxy universe. Here's a computer simulation showing how we think galaxies form. This is the birth of a big galaxy. And the thing this is a computer simulation again. The thing I just want you to see is it's a mess, right? This big galaxy cannibalizes so many smaller things. And again, the bigger it gets, the more gravity it has, the more things it can pull in. And it's just going to grow over time, get bigger and bigger and bigger. It becomes almost like a runaway effect. In fact, there are some galaxies, I won't talk about it tonight, called fossil groups. These are enormous galaxies that have no neighbors around. I study these for some of my research. And the idea is that these are the Hannibal Lecters of the universe. These cannibalized every one of their neighbors, and there's nobody left. So that's why there's big isolated galaxies with no neighbors. So as I said earlier, we can use the light of galaxies to map the distribution of mass and matter in the universe, just as we can use the lights of the cities on Earth to tell us how the land is distributed on Earth. So this is a map that was produced in the 1980s from work done by Margaret Geller and John Hucker in particular at Harvard University. Each dot represents a galaxy. And this was a Herculean effort because what they did was they measured the distance to all of these galaxies. And when you make a plot, you see that the galaxies are not randomly distributed. There's a pattern that you see. You see, for example, down here, this long line of galaxies. Up here at the top is same part of the sky done years later with the Sloan Digital Sky Survey. And again, you see these long linear kind of features we call filaments. This over here is called the Great Wall, the Sloan Wall, sorry. Just these huge structures that are visible, and these extend over many hundreds of millions of light years. They're just enormous structures. This is another image showing what we've come to call the cosmic web. And each dot here represents a galaxy. This is just one slice. It shows galaxies at a distance of, if I remember right, it's 100 to 200 million light years. And you see again these beautiful linear features. These sort of it's like a spider web in some ways. So we call this the cosmic web, and these things are what we call filaments. It's a very sort of delicate pattern. This is one of the best studied regions of the universe called the Perseus-Pisces Supercluster. And so each of these big clumps of galaxies here is one of those cities of galaxies they talked about, the Perseus cluster we talk about, for example. And you see, again, connected by this sort of thin sort of tendrils of galaxies. So the universe is anything but random on the largest scales. We know now that we reside in the outer regions of something called the Virgo supercluster. So here's the Virgo cluster I talked about earlier with thousands and thousands of galaxies. There's a bunch of smaller groups of galaxies, towns and villages surrounding it, much as there would be for any big city, right? And then our local group is out here. Again, we're about 50 million light years away. And there's other clusters, cities, groups of galaxies as well. But this is a map of what we think the universe looks like on these sorts of scales today. So we're getting a piece by piece again, we're getting a picture of where we live, what's our address in the universe. A few years ago, a group of Indian astronomers discovered one of the largest superclusters or super systems of galaxies yet found. It's called the Saraswati Supercluster. Saraswati is named for the Hindu god of knowledge. And it's enormous, right? It's this clump of galaxies here. And it's about 4 billion light years away from us. And as the arrow shows you, it's hundreds of millions of light years across. And although you can't see it, obviously here, it's estimated to have probably 100,000 galaxies or more. It's just an enormous system of galaxies. Another similar system is the Laniakea supercluster. This is discovered by Brent Tully at the University of Hawaii and his collaborators. And Laniakea is a Hawaiian word that means immense heaven. And it's like Saraswati. It's just an enormous system of many cities. It's almost like if you think about, cities clumped together into larger systems we call states, and states into countries, and all of that. So these superclusters like Laniakea are, even larger systems of galaxies. And in fact, because we can now measure the positions and distances of galaxies with a good precision, we can actually figure out which way things are moving in the universe. And there's pretty clear evidence that the Milky Way, the local group, the Virgo cluster, everything is being pulled by gravity towards some mysterious location that has been called the Great Attractor. So we're all flowing towards some distant region of the universe, presumably because there's a lot of mass over there and its gravity is pulling us over that direction. But there's pretty compelling evidence that this thing called the Great Attractor exists, and we're all falling towards it on the very, very largest scales. How do you get this kind of cosmic web? How do you get these enormous structures in the universe? It's actually truly amazing. It starts from little seeds in the early universe, really from quantum fluctuations in the early universe that get amplified by gravity over time to produce these kinds of structures and to produce this kind of network of filaments, this cosmic web. This is a computer simulation, again, showing if you put in tiny fluctuations, as we think might have existed in the early universe, you put in gravity in your computer simulation and you let the whole universe expand, this is what you get. You get this cosmic web, you get these filaments that link up together. And the yellow spots are the cities of galaxies. These are the clusters and groups of galaxies that form, usually where the filaments come together, basically. So we see that. Here's a computer simulation showing it's rotating, but it's also evolving over time, showing how we think this three-dimensional cosmic web looks like and how it evolved over time, right? So again, you see, so the Milky Way, so here, for example, might be like the Coma cluster of galaxies, and the Milky Way would be like a little group somewhere out here. Sorry, the local group would be a little group somewhere out here, for example. So, we have a pretty good understanding of how these things happen. And again, it's remarkable, from the smallest fluctuations in the early universe, gravity amplified them to produce these enormous structures that we see today. Just to go off on a tangent for a second, this sort of filamentary structure, this cosmic web, you see similar patterns elsewhere in nature. And it's one of the things I think is really cool is that nature recycles patterns in some ways. So this is actually an image showing neurons in the mouse of a brain, in the brain of a mouse. And again, you can see this kind of interconnected network, this sort of web that ties everything together in the mouse's brain. Looks remarkably similar to the kind of structure that I showed you earlier of the large-scale distribution of matter in the universe. Here's another example. This is the International Space Station image of the Belgian city of Liège at night. And again, you see these tendrils, these filaments, this network of light connecting together to the heart of the city, right? And that's very, very similar to what we see in a distribution of galaxies. And in fact, this idea of nature recycling certain patterns was reinforced really recently. I don't know if you saw this in the news just 2 weeks ago. There was a really cool story in Sudan. archaeologists have been studying for years these tombs of they're Islamic tombs from about 1,000 years ago. And they found that they're not distributed at random, they tend to cluster together, and they cluster together on different scales. And they tried to find a way to quantify that. And what they did was they borrowed statistical methods that astronomers have been using for a half century to describe statistically how galaxies are distributed throughout the universe. And they found that that kind of statistic, that kind of model that astronomers use to describe the distribution of galaxies also remarkably well describes the distribution of these tombs in the deserts of Sudan, which I think is really remarkable. But it shows, again, nature likes certain patterns. You'll find it repeated in many different areas, astronomy, archaeology, whatever. Here's another example, slime mold. So slime mold are colonies of single-celled organisms. They're amoeba in a sense, but they live together and they form tendrils that go out to search for food. And if you look at this pattern again, you see, well, it's a sort of interconnected, filamentary sort of pattern. Can we learn something from the way that slime mold grow here on Earth? Can you tell us anything about the way the galaxies and the distribution of matter on the universe grows on the largest scales? And the answer is maybe. These are some computer simulations of the evolution of the universe, a piece of the universe. And again, you see the sort of network of filaments, that kind of thing. And so it actually led these astronomers to write a paper not long ago, a year ago or so, where they actually used a numerical model of the way that slime mold grow in their search for food. And they applied it to the way structure in the universe grows on the largest scales. And they found it provided a really good description for why we see this network of filaments and this cosmic web around us. So again, the point was just to show that there's a pretty cool connection between the way nature works on very different scales and very different fields. So that's all I had to say. I'm happy to answer any questions. Again, my goal was just to give you a quick overview what we think the universe looks like on the largest scales. There's a lot of exciting stuff going on right now. James Webb Space Telescope is supposed to launch in October, hopefully, and that will change things pretty dramatically as well. But stay tuned. You know, our map of the universe is getting sharper and sharper every year. So I'm happy to answer any questions.
Thank you very much, Dr. West. That was a really great presentation. If anyone has a question, you'll need to either unmute yourself or you can put it into the chat. And Bob, if you're still there, would you mind reading the chat questions?
I don't mind.
All right,
I don't mind the line as long as I'm first.
Okay.
At any rate, I do
ahead.
have a question. Is there any evidence for either the Milky Way or the Andromeda galaxy to have been having experienced or being a composition of more than one galaxy? Any way to trace that? Now, this is amazing, all of this to me. I'm just wondering how our galaxy, what's the history on it?
That's a great question, Bob. In fact, I didn't have time to go into it, but there's ample evidence that the Milky Way is a serial cannibal. We see these streams of stars across the sky, which are the shredded remains of galaxies that got too close. And there are dozens of these streams known already. There's one now, even we see a galaxy being cannibalized by the Milky Way right now. It's called the Sagittarius Dwarf. And so as we've gotten better and better maps of the stars in the Milky Way through Gaia or through the Sloan Digital Sky Survey, we see these streams of stars. And just as I showed you that ghostly remain around that other galaxy before, and I said when a jet fighter breaks up, the pieces keep going forward, we see the stars in these galaxies that have been torn to pieces by the Milky Way. We see them in these streams across the sky, and there's dozens of them known, and they will disperse over time. So there must have been more in the past even. So our Milky Way has definitely cannibalized other galaxies. Same thing with Andromeda. There was a really good survey done over the past few years with a telescope in Hawaii, and they mapped those streams of stars around the Andromeda galaxy, and you see loads of them. So every sizable every galaxy picks on a smaller galaxy to confine one, basically.
Okay, thank you. We just had just a sidebar here. I don't know about Mark. We're not too far apart. They're having tornado warnings right now. So I don't see anything, let's see, on the chat, right? So anyway, if we get cut off, Wayne, you're a co-host, maybe you can pick it up. Oh, here, I do have one. Yeah.
Bob,
Yes.
the sirens are going off in my neighborhood for the tornadoes,
Okay.
so I'm gonna leave you.
All right.
Stay safe.
Talk to you later.
We'll hang in here a little bit. First question's from Uriah in Lansing to everyone. What wavelengths of light are observed in the telescopes in Flagstaff and the greater Flagstaff area?
So that's a good question. The telescopes for public viewing are all optical telescopes. They do visible light. Out at our telescope, the Lowell Discovery Telescope out in about an hour outside of town here, we have instruments that can detect visible light, but also infrared light as well. So we have we do both out there.
Yeah, excuse me. He adds, he means electromagnetic wavelengths.
Yeah. So I mean, it's
So-
most of the instruments do visible light, but some of them do infrared light out there. We have an infrared
All right.
spectrograph, for example, and we're getting a brand new infrared imager actually, which will be really nice.
Great. Anybody else want to switch off their mute and join with a question? I don't see any on the chat list. Also, the collection of this data for such an immense field of galaxies, just it amazes me that we've been able to map it like that. And I can't imagine what could have been done without any computers.
Oh, sure. Yeah, I mean, I'm old, so when I started in graduate school, astronomy was still data starved, right? There just wasn't enough. There was never enough data. There were never enough photons, and it's changed so dramatically in the last few years with, Sloan Digital Sky Survey and NED. I don't know if you've ever looked at the NASA Extragalactic Database. It's mind-boggling. It's got data for so many objects, and now, of course, with the LSST, or the Vera Rubin Observatory coming online, it's going to map the sky. It's going to take a video of the sky every night, essentially. There's going to be so much data. Astronomers are drowning in data at the moment, and it's a great place to be. But yes, but for computers, again, when I started graduate school, we had an old computer, a PDP-11. Your drive was about this big, and it held about 100 megabytes or something.
Oh, yeah.
Put it in the computer, and now you get a 1 terabyte drive in your cereal box practically. So it's really changed a lot.
Good. We have a question from Gangadeep Care, if I pronounce that correctly. Excuse me. What happens to the planets when two galaxies collide?
That's a great question. So generally, absolutely nothing. Again, the distance between the stars and their planets is so great that they won't collide, and they won't even pass near enough to each other to really do anything. So again, when the Milky Way and Andromeda collide in the future, for example, it'll just be one big happy family at the end. I always think of the sun like a mother duck with its baby ducklings in tow, all the planets will just come along with the sun and become part of this new bigger galaxy. Nothing will happen to them, except for the fact that the sun will be dying at the time and it's not a cool place to be. But other than that, nothing will happen at all.
All right. A question from Uriah again. What data are you generally working with and compiling in your role?
That's a good question. So I use Hubble Space Telescope a lot for my research. I have a couple of projects going on there. So for example, one of the projects I'm working on with Hubble, we just published a paper, and we're also using the Lowell Discovery Telescope because I can get a lot of time on that because it's our telescope. We're looking for these cities of galaxies, these clusters of galaxies, but we're trying to find the first ones. It's like if you're an archaeologist and you want to find the first human settlements, first human civilizations, how cool would that be? And so we're trying to do that with galaxy clusters. When did the first cities of galaxies form? Was it 1 billion years after the Big Bang? Was it 5 billion years after the Big Bang? And so we're trying to do that using Hubble and using our Lowell Discovery Telescope as well. But like most astronomers, at any given time, I have like 4 or 5 different projects I'm working on. I work with the colleagues in Finland a lot. So we have a student in Finland working on a project with us right now using some data from Hawaii. But most of my data is, most of my observations are optical, the visible light again, but I do some observations with with infrared as well.
All right. Gagan Deep again asked, at which place are you planning to build the Lowell Astronomy Research Center?
Good question. Sorry, I should have been clear about that. It's right here. So our main, we call it our campus. Our main offices are right in Flagstaff, a place called Mars Hill. So we're like 3 minutes from downtown Flagstaff. Not a good place to put telescopes. That's why we don't. We've got our main research telescopes about an hour outside of town. So the Lowell, the Astronomy Discovery Center for visitors to come to, that will be right here on campus. So right in the heart of Flagstaff, basically. And again, light pollution isn't a big problem, even in Flagstaff. We're a city, if you include all the surroundings, we're about 80,000 people. And I walk my dog every night. I live right in the city. I can see the Milky Way on any moonless night from when I'm walking. So we really don't have an issue with light pollution out here.
Any other questions?
I encourage you all to come out to see the new Astronomy Discovery Center when it opens in 2023. It'll be pretty awesome. And if you come out, drop me a line. I'm happy to show you around.
All right. Any other questions? You're welcome to unmute and ask. Mark, pardon if you see Mark or I leaving for a moment. Apparently there's a tornado. It did touch down. It's 8 miles west of Pontiac, which is probably maybe 15 miles from here. But anyway, keep going. If anybody has a question, please go ahead and ask.
I see a question from Felix. How long does it take the Sloan telescope to map the whole sky? So Sloan's been doing this for years and years, and it can't map the whole sky. It only does, like the northern hemisphere. Essentially, it's located in New Mexico, and but it's been doing this for years. I think they're on their 16th data release. So for at least 16, 17 years, it's been observing the sky. And you can get all the data if you just Google Sloan Digital Sky Survey. You can download any images you want. It's incredible. So it's Sloan. I forget. There's like 10,000 published research papers based on Sloan data. It's just mind-boggling because you can do so much with it. But it's been a Herculean effort to do that. But it's really revolutionized astronomy.
But it's been operating, you say, for 16 years, but it's mapping the same thing over and over again. How long does it take to get one image of the entire northern hemisphere?
Oh, that's a good question. I'm not really sure. You're right. What they do is they cycle through different filters, for example, so you get different color information for all the objects it detects. Yeah, at this point, I think it's true. It's not covering new ground. It's going deeper for one thing, and it's getting different filters that it might have missed. I don't know. To be honest, I don't really remember how long it takes to do one, swath of the sky, one whole area of the sky that it's doing. I don't remember offhand. I mean, the problem with Sloan is if it's cloudy one night, they got to go back and do that one again. If the seeing was really terrible, they got to go back and do it again. But it's just incredible how they've done. In fact, I don't remember if Sloan actually did drift scanning. Drift scanning is when I have to think about this. Whether you point the telescope or you keep it pointed at, say, the zenith, and as the sky drifts over, you just continuously reading out the data, and you can build up images that way without having to keep pointing at different parts of the sky. But I don't remember off the top of my head which one Sloan was using.
Has the smoke affected you much this year?
Out here, it was for a while. It was really bad. We had to close the telescope a while. We actually have a monitor that detects the number of particulates in the sky, and we had to close every summer. We have to close for a few days because of smoke from nearby forest fires. Because we've had the monsoon rains for the last 2 or 3 weeks, it hasn't been a problem. But there was a bad fire out here up until pretty recently, actually. So yeah, that's one of the problems we have. I always say, everywhere I've lived, there's something will get you. Here in Arizona, it's forest fires or rains. I lived in Chile where it was earthquakes. I lived in Hawaii where it was tsunamis. So somewhere something is trying to get you. You guys got tornadoes at the moment in Michigan. So.
Bob, I think, is going downstairs.
Yikes. Okay.
Yeah, he's muted. Bob, you're muted if you're speaking.
Oh, okay.
Yeah.
Sorry about that. Yeah, I'm heading down to a lower level. The rain's pretty hard. I was just looking for hail, and that's a good clue to better get pretty low. So,
Did you see any?
No.
Good.
But
Well, stay safe.
Are there any other questions?
well, we have let's see, from Uriah's thanking Dr. West for presenting and for Seven Ponds for hosting. So you're welcome, Uriah. Thanks for coming back.
Yep. Thank you for joining us.
And any other questions? I'm going to try to stay online. It depends on how the goodness of my Wi-Fi signal.
Right. Right. Great. Well, thank you, Dr. West, again for joining us. That was really an excellent and interesting presentation. I think we all enjoyed it.
Thank you. My pleasure. Thanks for the good questions, too.
And thank you, everyone, for joining. I'll stop the recording at this point.
Excellent. Excellent. Thank you.